Yeah, Rahil, you're visible clearly and audible also.
Yeah, I'd be requesting some of the people who are there in the meeting to as well turn on the cameras so that it can be an interactive session. Okay. So, hi, good evening, everyone. My name is Raahil Sheikh. I'm currently in the third year of my aerospace engineering, and I'm also a astronomy geek. At the same point, I'm very much interested in aerodynamics and, you know, astrophysics as well. So these are some of my interest in this particular field, and today I will be your host and the speaker. So why don't we let anyone else introduce themselves? Karthik.
Hello guys, am I audible?
Yes, you're audible.
Greetings everyone. I'm Karthik and I'm a huge fan of astrophysics, anything related to space, and that was my sole reason to join on this workshop and learn more about, especially more about aerodynamics.
Okay, that's really great. Aditya.
Am I audible?
Yes.
My name is Aditya. I'm first year aerospace student, and I am always fascinated by aerodynamics and aerospace. So yeah, that's the reason I joined this course.
Okay, that's really great. Can we have someone else as well introduce themselves? Some Aditya, I guess.
I am from Hex-Star only.
Yeah.
Hello, am I audible?
You're audible.
Yeah, good evening, everybody. Myself is Manjita Mitra. I'm a first year aerospace engineering student, of course, in CU. And to be very frank, I'm not somebody who, like, I do not have a plethora of knowledge about this field, but I kind of developed my interest in this field after getting inspirations from various, sources. And here I am to know more about it, to kind of know about the path which I should work on, to know everything that I really want to know and find out what I'm really interested in. So yeah.
That's really great to hear, and I hope that you do find your interest in this particular field. Srinanjay, are you there?
Okay, I think now we can start off with the session because the stream has started. So I
Okay,
would request Rahil to start off with today's session.
okay, sure. I'll just start with the screen sharing. Yes, is the screen visible to everyone?
Yeah, the screen is visible.
Okay, so good evening, everyone. I'm just going to do my introduction again. So here I am, Raahil Sheikh, going to do the fundamentals of aerodynamics. And aerodynamics in itself is a very interesting field of study since it is the study of how gases interact with the moving bodies. Now, this moving body could be anything as we perceive. It doesn't have to be a moving body. It could be a stationary body as well, depending upon how big the mass is. Now, to think about it, can anyone just describe what does aerodynamics means to them? What is the fundamental meaning? Karthik, Aditya.
The way an object moves in air, maybe.
Okay.
Yeah.
The word dynamic refers to various kinds of movements, I guess. So it's about the variety of movements which an aircraft experiences or like it has to perform when it is in flight.
Okay. I mean, the fundamental idea is more or clear that whenever an aircraft moves, the flow which is going over it is basically aerodynamics. Now, aero is basically the movement of air over any sort of particle, and dynamics is the study that we are doing, like dynamic study. Now we have static and dynamic. I'm pretty sure that the fundamental idea is clear regarding the both. So to move ahead, I'll just discuss in brief what are the topics that we'll be discussing today. So firstly will be the fundamentals of why aerodynamics and what are its significance. Then secondly are the experimental aerodynamics, that what are the current experimental methods which are being carried out. Thirdly is subsonic to supersonic ranges in aerodynamics, that is one of the flow regimes which are usually observed. And lastly is the hypersonic range. Right. So right. So first things first, the fundamentals of aerodynamics, like the basics. Now, usually we prefer that Ludwig Prandtl is marked as the father of modern aerodynamics. But according to me, that the first aerodynamics study was observed much before that. That was in second and third century by Aristotle and Archimedes. This was done in order to find out how flow is moving over a bird or an insect, how they're flying in air, what sort of wing they are using in order to fly. Sir Ludwig Prandtl was back in 17th century discovering how heavier than air aircrafts are able to fly, or they can be made to fly. Right? Aerodynamic discusses about the flow over or within a body or object within a system. Now there are two types of differentiation in this. There's external aerodynamics and internal aerodynamics. The simple differentiation being that if I keep any sort of object which is present in a system, right? When flow is moving over it, then it is external aerodynamics. And when we're talking about internal aerodynamics, that is, let's assume like a flow inside a nozzle. That can be termed as the internal aerodynamics part. Now, the reason why we're studying aerodynamics or the importance of it is that we can reduce drag, noise emissions, and prevent undesired forces. These three are the most fundamental reasons why aerodynamics is important for an aerospace engineer. And later on, you can also understand why it is there for, sole physics purposes as well. Okay. Now, I would like to discuss about the flow regimes. Now, there are four basic regimes in aerodynamics. That is subsonic, sonic, transonic, supersonic, and hypersonic. Now, as the images are visible, that subsonic is the range where the Mach number is less than 1. Then transonic is the range where Mach number is between 0.8 to 1.2. And up, that is up to Mach number 5, it is the supersonic range. And above Mach number 5, hypersonic. Now, can anyone tell me which is the fastest aircraft till now? And by aircraft, I don't mean rockets, but aircraft which are, ranging in supersonic range.
Concords or SR-71?
SR-17. Okay, that is the older version. Any new guesses?
X-15.
Yes, X-15 is the recent supersonic range fastest aircraft. At this current moment, people are also working upon hypersonic flight, and that is a much achievable flight, but at the same point, losses are very much high. Now, what do I mean by Mach number? So Mach number is basically a way that we are observing movement of air, the flow of air. That is, m is equal to v by a, where v is velocity of an object and a is speed of sound. You're using speed of sound as a reference in this particular calculations for Mach number. It's because of the fact that when an aircraft is moving at very high speed, that is, let's just assume Mach is greater than 1, it is going faster than the speed of sound. The moment we are going faster than the speed of sound, there are bound to be pressure disturbances in the flow. And that is one of the reasons why we can observe that there is shock waves behind an aircraft or fighter jet aircraft, moreover. Now, to talk about the types of flows, there are 6 fundamentals. One, that is steady, unsteady, uniform, non-uniform, laminar, turbulent, compressible, incompressible, rotational, irrotational, and 1D, 2D, 3D flow. Now, talking about steady and unsteady flow. Can anyone just guess what could be the meaning of steady flow?
A
Let's
continuous interrupted flow.
okay, continuous and uninterrupted flow. Okay. Any other guesses or ideas? Let's just use an example. We are taking a pipe, okay, and within a pipe there's flow going, right? And that flow is, in the subsonic range. We aren't putting any particular flow regime. Now that flow or the flow characteristics. Now there are three basic characteristics of the flow. That is velocity, pressure, density, and one more which I can't remember at the point. So these characteristics, when we are measuring with the rate of time, so it is steady flow. With the rate of space, then it is uniform flow. This is the only difference between steady flow and uniform flow. And I hope it's clear with everyone. Okay. Now, laminar and turbulent flow. Could anyone try to give a guess regarding that? What is the meaning of laminar?
A streamline flow.
Streamline flow. Okay, that is a good construct we can use upon. Any other guesses for laminar?
Laminar flow is usually smooth and it doesn't break. I mean, it's regular. It keeps on
Yes,
going.
that's correct. So laminar is again a flow regime which is being observed, and that is moreover observed when the flow is, uniform and it is not having any disturbances when it is flowing around an object. Now, laminar turbulency can be very much solely dependent upon Reynolds number. That is a factor which is mainly used in fluid mechanics and aerodynamics. That is the inertial forces to viscous forces. Now, if the Reynolds number up to a certain limit, if the flow is, after doing the calculations, you're getting the number less than 2,400, the flow is said to be laminar, and if it's more than 2,400, then the flow is turbulent. Now, compressible and incompressible flow. Let's take an example of a book, right? A book is a solid object which has particles present in it. Is the book compressible or not?
It isn't.
It is incompressible. Okay. Is liquid compressible?
Till an extent, yes.
Okay. And are gases compressible?
They are the most in comparison to
Yes,
solid
they are.
gases.
Yes. So the whole concept of why we are studying compressible and incompressible flow is because that when an aircraft, any sort of uh, rocket or any missile is moving through air, compressibility is the reason why it is able to move through. That gas is the medium. Now, when we are talking about compressible flow and incompressible flow, there's a basic difference in terms of aerodynamics that if the density variation is less than 5%, then we are terming it as incompressible flow. And when the density variation is greater than 5%, then the flow is compressible, right? Compressible is more the fact that if you're taking any book or any sort of medium, that is, let's just say, assuming gas, and you're pressuring it down. So the intermolecular forces which are present in it, they get reduced. And that is more of the definition of compressibility. Solid objects are not bound to be compressible as the intermolecular forces are very less, right? So that thing is also clear. Now, rotational and irrotational flow. Rotational, okay, let's just say that we have a cricket ball, right? When a bowler is coming at a speed and it is throwing the ball, if the ball is being kept at a straight seam and it is being thrown, so that is an irrotational kind of flow. But at the same point, if a spinner is throwing the ball, then the ball getting rotated through the air, right? So that is an example we can use for a rotational flow. Okay. Uh, I am using some terms of cricket because I'm very much adverse with it. But is there any doubts regarding rotational and irrotational flow? Okay. Now one-dimensional, two-dimensional, three-dimensional. Right? So 1D flow, if we have to define it as people who do play games, I'm just going to say it in that sense. Uh, let's just start with 2D first, right? So we know that there are coordinate systems, right? Polar coordinate system, Cartesian coordinate, and cylindrical coordinate system. If you're talking Cartesian coordinate, If we have the x-axis and the y-axis, then it's a 2D system. If we have just the x-axis, then it's the 1D system. And if we have a three-dimensional flow, then it's the x, y, and z, right? So is that clear? These are just the basic fundamentals. And whilst you're learning about it, you can also understand more that how these functions are correlated to each other and what are the functions. Like there are two basic concepts which are being used, that is stream function and potential function. Once you get to know about that, that is very mathematical based, so I won't dwell much into it. So you can understand the types of flow that we can differentiate between. Now, can everybody see this picture over here? That is of an airfoil and a cylinder, right? So could anyone just explain what is going on in this picture? Just a random idea.
Is it creating a vacuum?
Sorry.
Is it creating a vacuum?
Okay, vacuum as in the sense, like, could you explain the word vacuum over here?
Like free space, or there's no flow or something like that?
Okay. Would anyone like to take a guess over it? Or what is the interpretation of these two images?
Vortices.
Vortices. Okay. Now, if I have to explain this, moreover, the fact that the reason why airfoils, okay, so airfoil is basically a special sort of structure which is being used in wings, right? Any sort of wings have a aerofoil, and that aerofoil can be represented with the help of NACA series. Now, aerofoils are a special shape which are made from circles or cylinders, right? They are transformed into a cylinder. Now, if I have to explain it in the sense, like there's a cylinder which is kept over here, and all the points which are present on the x and y axis, they are being transformed and elongated to make an aerofoil. So aerofoil is just a special shape which is made out of a sphere or a cylinder. This is done with the help of conformal transformation. Now, this is a representation where we can transform objects into another being, and you can even do a representation of black holes with the help of conformal transformation. So this is a very good research topic. One can surely go through it. Now, to discuss upon this particular image, what I wish to explain is the fact that is the flow going behind it. Can everybody see the blue shaded region? According to between the two of them, which shape will be creating more drag, or will be having more, distractions behind the surface of the body?
The ball, maybe, I guess.
Okay. And why do you think so?
Because it's sort of, I'm just guessing, because it's sort of blunt and not pointed out.
Yes. You said a word called as blunt, right? So what does blunt mean in this particular sense?
Blunt mean that we can clearly say that only one of them would be cutting through air and other would be like pushing inside the air, and the other, like airfoil will be cutting through air and the ball will be pushing. And as we see in the aeroplanes, they have a sort of pointed nose so that it helps. I mean, if we put not pointed nose or something else like a blunt ball, so that when it would consume more fuel and it would take more energy to cut through air.
Yes. So whatever you have explained, I'll just add to the point that the basic difference is a bluff body. Now, when we are talking in aerodynamics, bluff body is any sort of geometric shape. It can be a cylinder, a rectangle, or a triangle, which is high wake region. Wake is the region which is created after the disturbances are created after any surface. Now, if I have to show, this region or this part is the wake region where all the disturbances or vortices are created. Now, as you can see, aerofoil does create a wake region, but it is very narrow because uh, at the trailing edge or at the the intersection, the edges are getting swept or they're getting very slim through. and that is why the wake region which is being observed is very slim. At the same point, due to the cylinder being a bluff body, we can see that there's high amount of wake, and at the same point, due to the high amount of wake, we can see high amount of vortices which are being created. Okay, so are these two fundamentals cleared, and what are aerofoils, bluff body, the flow regimes, and the types of flow? Right? Any sort of gibberish that you guys didn't understand? Okay, let's move on.
As this barn owl glides.
Okay, so this is a short video that I want everyone to go through. If you are unable to hear the audio, just let me know. Okay.
Through the darkness, a sudden flash of light illuminates over 20,000 helium-filled soap bubbles suspended in the air. Researchers can track the bubbles as they swirl in the owl's wake, and they're using this to study the bird's flight in unprecedented levels of detail, revealing unexpected ways in which birds generate lift and reduce drag while gliding. The first task is to persuade the birds to fly through the cloud of bubbles. If they can see the bubbles, they try and avoid them, so the researchers have to snap the lights on right at the last minute. That's the idea, anyway. When the birds do glide through smoothly, they leave vortices swirling in the air behind them. The movement of each bubble is then tracked and recorded by a computer to visualize the airflow. As expected, the researchers saw vortices spinning down from the wingtips. This helps provide lift. But the swirling bubbles revealed something surprising. A second pair of vortices coming down from the tail. These also generate lift.
Right. So the brief interpretation of this video is that if we are taking any insect or a bird, and when they're moving through air, they're creating vortices. Now, vortices are also a region why lift is being generated. At the same point, they're also the reason why drag can be created onto that particular flow. Now, that particular thing, the vortices which are being observed in the flight of a bird, that can be clearly seen in that of an aircraft. As you can see that there are vortices which are being curled downwards, right? Now, as any aircraft is moving through air, vortices are consecutively being generated. It's not the fact that if wind is going over an aircraft and the vortices are being created, there's always going to be vortices being created, flow separation being occurred. But at the same point, vortices are also the reason why lift is being generated. Now, to explain why vortices are getting created, so I'll just use a small model which I have right now. Is everyone able to see this small aircraft? Right? So if this is the ground level, right, and the aircraft is moving this way for its takeoff, now the wind will move towards it, right, and the wind at the ground, like during takeoff, the wind will be hitting these two edges, right, these two. Now, when the wind is hitting these two edges or the winglets, moreover, there's a swirling action which is happening behind the aircraft. Because of this swirling action, you can observe that vortices are being generated. This is the most fundamental idea that how vortices are being created. Basically, whenever flow hits any surface or any sharp edges, because of the swirling action and the high speed of the aircraft, vortices are being generated, and we observe the vortex sheet, right? So, is the whole concept of vortex, understood by everyone? Yes. Okay. So let's move on. Okay. Now, let's try to, guess this part, the aerodynamic phenomena. Vortex sheet, I already explained that when at high Reynolds number and object is placed, like let's just assume this particular bird, when the Reynolds number is being increased, the flow gets separated, and we can observe a wake region where the vortex sheet is observed, right? Now, this particular first point is clear. What is boundary layer? And where can we usually see a boundary layer on any object? Any guesses? Or can anyone just explain what does boundary layer even mean? Or after reading the two terms, what can anyone interpret of it? Samaditra, Karthik, Aditya, Sona.
A liquid or like a gas which is in contact with the surface of the aircraft, maybe.
Yes. So that is the correct explanation for a boundary layer. That is moreover a layer over any aircraft or any body which is moving through air. Now, the reason why boundary layer, phenomena is more important. It's just the fact that at high speeds, this boundary layer gets distorted. By distorted, I mean that there'll be a difference in pressure due to which you can observe a high amount of turbulence, right? So even during harsh weather, there's a chance that the boundary layer over an aircraft, just going over the wings, the flow gets so turbulent that the boundary layer gets disturbed and there's a pressure difference which is being created, or disturbance moreover. Now, third is shock wave. We've always heard the name shock waves multiple times. You often associate it with sonic boom. Shock waves are, in simple terms, it's basically like a pressure disturbance in the same sense, but that is very much particular to or peculiar to supersonic and hypersonic range. This is again in terms of when an aircraft moves faster than the speed of sound. Speed of sound is basically 433 meters per second, and when Mach number is greater than the speed of sound, we observe a shock wave. Shock waves are also observed when you are doing testing of any rocket engine. That is, we observe a shock diamond in its flow, and that is a very different phenomena because it's regarding the underexpanded nozzle and overexpanded nozzle and oblique shock waves moreover. So in general in aircrafts, shock waves are more observed in hypersonic and supersonic range, and in simple terms they are the pressure differences or disturbances due to the high Mach number. Okay, so does anyone have any doubts regarding vortex sheet, boundary layers, or shock waves? Okay, we shall move ahead. So, coming on to the experimental part of aerodynamics. Now, there are two methods where or how we can test an object moving through air. Firstly, being wind tunnel testing, and second is computational fluid dynamics. Now, to talk about wind tunnels, so wind tunnels are basically like a very big, cross-sectional area where we have a honeycomb structure, after which there's a settling chamber, the test section, the diffuser, and the outlet. Now, the reason why I'm explaining these weird terms is because of the fact that whenever we have to, visualize the flow over any object, whether it's in supersonic or subsonic region, we use a wind tunnel. Wind tunnels are very largely used in aircraft models, and those are the reason why people are able to develop or test their prototypes moreover. Now, in case of any aircraft which is being made, let's just assume that Boeing has made a new aircraft and they have a design. So they will scale down the model, they'll make a small prototype, and that prototype will be kept in a wind tunnel. And the reason why it is being kept in a wind tunnel is they wish to see how efficient is the lift creation at different angle of attacks. Angle of attacks, if I have to just explain, is that if this is an aircraft, this is basically a zero lift, zero angle of attack, right? Now, when the pitch is getting shifted upwards, the angle of attack increases. So, angle of attack is moreover the angle between the relative wind and the chord of an aircraft, right? So, these two things are very much required to judge the wind tunnel testing and whether to know that the testing that you're doing is valuable or not. Now, second comes the computational fluid dynamics. So CFD is not just restricted to aerodynamics. It's more than that, because with the help of CFD, you can analyze static structure, STK, and even aerodynamics. Aerodynamics, when it is moved to CFD, we use FEA, and there are many other methods. So it is a method to visualize flow, and it can be done by engineer students with the help of their laptop, right? So I'll just move to the next slide to give. Yeah.
Boundaries of the flight envelope, where flow conditions are.
So this is an actual, Boeing model which is being under simulation, right? And you can see how the flow is moving over the wing, the type of vortices which are being created, and the flow regimes, right? So that is the thing that you have to observe in this video, and you can understand why CFD is more important. Okay.
Highly dynamic. For example, takeoff and landing, buffeting, or aerodynamic degradation from icing conditions. Traditional fluid simulation tools struggle with these configurations, and physical tests are still the standard. This leads to expensive and time-consuming development, delays in flight certification, and increasing cost and risk.
Now, this particular method, or the way that the aircraft is kept inside a tunnel, so that is more or like a wind tunnel testing. Moreover, that a high, uniform amount of air is flowing at the aircraft, and we can visualize how the flow is going. We even use a smoke generator. Smoke generator helps visualizing the flow streamlines over the aircraft wing or any sort of airfoil structure as well.
In developing future concepts. But Simulia fluid solutions offer a breakthrough in accurately predicting the highly complex and unsteady flow phenomena that determine aircraft characteristics for all of these situations. Of particular importance is the ability to understand how airflow over the wing breaks down at very high angles of attack. Simulia fluid solutions are able to assess the impact of extremely complex geometric details on flow behavior, the influence of the jet engine on the high lift system, and buffet onset at high speeds, boundaries of the flight envelope, where flow conditions are highly dynamic. For example, takeoff and landing, buffeting, or aerodynamic degradation from icing conditions. Traditional fluid simulation tools struggle with these configurations, and physical tests are still the standard. This leads to expensive and time-consuming development, delays in flight certification, and increasing cost and risk in developing future concepts. But Simulia fluid solutions offer a breakthrough in accurately predicting the highly complex and unsteady flow phenomena that determine aircraft characteristics for all of these situations. Of particular importance is the ability to understand how airflow over the wing breaks down at very high angles of attack. Simulia fluid solutions are able to assess the impact of extremely complex geometric details on flow behavior, the influence of the jet engine.
Yes, sorry. So now this particular thing, that the flow inside a engine is more important. That particularly that air breathing engines, like let's just assume we are talking about a Boeing engine, and there's a difference between air breathing engines and non-air breathing engines. So usual aircrafts that we are seeing, the commercial aircrafts, they are air breathing engines or propeller driven, and air breathing engines have compressors or nozzles which uses the air at a very high compressed region, and they use that to mix fuel. And that is being, the basic concept of any bike or a car, that highly compressed air gets mixed with the fuel, and that is being used as the propellant over there, and that is used to generate high amount of thrust. Now, the reason why simulation of an aircraft engine is also required or important is because at particular regions there's surging and choking of the engine. Now, what I mean by surging and choking, they're the regions where the flow gets reversed. Now, you might think that this isn't possible, but when you study about compressors, that is axial flow compressor and centrifugal compressors, So actual flow compressors have this particular stage where the flow gets reversed, and this is very harmful for the engine because at that particular point, the amount of pressurized air which is required for the fuel and air mixture that isn't getting elaborated or required, that efficiency, and the efficiency drops down. Surging and choking is hardly like a millisecond thing or a phenomena, but at the same point it's very much harmful for the aircraft because the more the efficiency gets down of the engine, the it will be requiring more maintenance, and for any airline that is the worst possible case, right? So that is the reason I've paused this video. Now let's continue.
On the high lift system and buffet onset at high speeds, allowing you to predict stall with proven accuracy.
Now, as you can see, the flow over here is totally turbulent, right? That the flow behind the wing, it is, not laminar, the streamlines aren't proper. But at the same point, the aircraft is moving at such a high speed and such a high height, it is not experiences, much sort of differences or any sort of derogatory perks. Can anyone, like explain the idea that even after the flow being so turbulent, the aircraft is moving so smoothly in the wind? Has everyone understood the question which I'm asking? Yeah. The fact that even at high speeds, why do wing structures don't break? We know that at particular high speeds, the aircraft, any sort of wing, it will undergo buckling, right? And because what is a wing? It is basically a cantilever structure. This is the fuselage or the fixed part, and this is the wing. At any sort of high speed or high flow regime, there will be high amount of pressure which is acting in the center of the wing, right? And even if the flow is going over the wing, we can obviously see that the flow is very turbulent. In that sense, an aircraft shouldn't move in the air, right? Because if so much amount of gravity or backward force is acting on any sort of wing or aircraft, it can't move in air at that particular region. Like, um, so does anyone have any idea that why is this able, that aircrafts are able to move in air, or why they're able to, counteract that high flow regime?
I've seen a video where they show that the wings are kind of, flexible and they sort of move with the airflow. And they're not that brittle and hard so that the wing breaks them, but they're sort of flexible. And during, when taking off or while landing, the wings, they have, small flaps at the back, which they move up and down. I've seen that. So maybe that's the reason.
Yes. So on a wing, that is a very correct explanation. There are flaps, which are high lift devices, and ailerons and elevators. Those are different things. So on particular the wings, we have ailerons and flaps. These are basically high lift devices. So basically, when the flow is going over a wing, the particular flap or the ailerons, they move or they adapt to the flow, and due to the pressure difference we are able to create that lift, or an aircraft is able to move upwards, right? If I have to show you guys an image, just a minute. Okay, so this particular region on the wing is the flaps and ailerons. Due to the reason why, even at a high amount of speed or high amount of flow regimes, we're able to observe lift, right? These are controlled by hydraulics, and because of that, we are able to move through air smoothly. And during takeoff, even though there's a lot of wind disturbance acting on the aircraft, we're able to, go means go through it, and the same point, with the angle of attack we are able to increase our elevation, right? So that is the whole point of this. Now getting back to the presentation. Yes.
sea. Simulia Fluid solutions on the 3D Experience platform allow you to develop digital prototypes through virtual testing of real-world designs. By coupling dynamic loading between fluids and structural simulations, you can assess the impact of component deflections on aerodynamics, greatly improving and strengthening your design. Simulia Fluid solutions allow you to augment and often replace physical tests. You can also receive insights.
Now, we read something known as degradation due to icing, right? Now, has anyone seen the movie Iron Man, the first Marvel movie of Iron Man, right? If you have seen in that, at a particular altitude, there's an icing layer which is being developed on the suit of that particular, character, right? So in the same manner, when the aircraft is moving at that particular altitude and it is moving at that particular speed, icing is being generated on the wings, and it can be harmful because if there's a rigid structure, and icing is obviously not going to be uniform, right? If this is the wing, the icing can be just present on the surface, due to which the flow separation can occur, and it can be dreadful for the aircraft at any particular speed. So in order to avoid icing, there are multiple methods, and means we aren't going to go into the depth of it. But yes, that is something that people are also researching right now. That even after going at supersonic speed, there are possible you know uh, problems of icing which are faced on the winglets and even the surface of the aircraft. Now, continuing with the video.
Into flow behavior that are simply not possible from physical testing.
Yes. So, particularly for icing or any sort of problem, physical tests aren't possible because it's more the fact that we can't create a simulation or any sort of physical test which is at that particular elevation and that particular speed without actually moving, right? So, even if you're making a wind tunnel which is being, kept at that particular simulation, moreover, icing cannot be generated in that particular wind tunnel testing. It is obviously a phenomenon which is observed when we are actually flying the aircraft or any sort of rocket or something, right? So, is everything clear about this video, everyone? Any doubts? Okay.
In boundaries of the flight envelope, where flow conditions are
Right. So, this is the wind tunnel that I've been talking about so much, not sponsoring it. But at the same point, a wind tunnel is very much essential when we are talking about the aerodynamic experimental study. Now, the one that you can see on the left, that is the subsonic wind tunnel, which is even present in many universities for testing. You can put up a small scale aerofoil or wing, even a small RC model, and do its testing. The So this particular structure is known as the honeycomb structure. It is used to laminarize or uniform the flow. This section over here is used to strengthen the flow. Now, when I mean strengthen the flow, it's more the fact that it is a chamber where the flow gets collided with each other, and the uniform flow gets constricted. So the moment the flow gets strengthened, means it's basically like a collection hub for all the air particles, right? After that, we have this constriction. Now, there's a basic relation that we know, that as we increase the area, the velocity decreases, and as we decrease the area, velocity increases. This similar concept is very much visible in nozzles as well. That the effect is itself known as Venturi effect. That in any sort of CD nozzle, if you have seen, that the flow is moving from the inlet to the outlet, and in between there's a throat region. Now, because of that particular constriction or degradation in that area, we're able to observe that high amount of thrust or high amount of velocity. So that particular same principle is being applied over in wind tunnels, where that constriction is being made to increase the velocity of flow that is going to hit the particular aircraft or the model in testing, right? And this is the diffuser. Diffuser is more in the sense to just make sure that the flow is leaving properly, and diffuser has many different applications in aircraft than that of a wind tunnel. And lastly, this is the wind turbine, or more of the rotor, with the help of which the flow is being generated. Now, the configuration of honeycombs is also very much required or essential, because there's the square, hexagonal, and the circular one. Now, according to just a general idea, which one could be the most efficient one to get the higher amount of accuracy? Would it be the circular, the hexagonal, or the square one? You can even take a random guess. There's no issue that you have to think the aerodynamics or something, or about the shapes.
Hexagon.
Sorry, Aditya, could you repeat?
Hexagon.
Hexagon. Okay. And do you have any possible reason for why it could be a hexagon one?
As it is the strongest shape, I guess something will be with that.
Okay. Karthik, according to you?
Probably hexagon because it's the more. I mean, it's not circle or square. That's it.
Okay, I understand that hexagon is a different shape and it's not the usual kind. Yes, to some extent, hexagon is the correct option or the reason, but usually squares are usually used in the wind tunnels, and even cylindrical ones. But the whole purpose regarding the square honeycomb structure is because that if we are using a hexagon kind, there are multiple sides to the honeycomb structure. As you can see over here, there are 6 sides present over here on any single hexagon. If the flow is getting hit at any one edge, the flow is going to get disrupted, right? We need a very laminar flow. We don't need disturbances at the entry, moreover. Similarly, for the rectangular one, there's a disadvantage that in between there's a chance that it is going to hit the edge and then go inside, but it is comparatively lesser than the cylindrical and the hexagonal one. Particularly for the cylindrical one, there are going to be gaps in between, and the air can escape through it, which is again detrimental to the whole point, right? So usually we use square ones, but at the same point, hexagonal ones are being implemented, right? So this was the subsonic wind tunnel, and this is the supersonic wind tunnel, right? And this is the one which is being used in USA and China, and again the applications are there for aircrafts and any sort of missiles testing, right? So the experimental use of aerodynamics has been clear with everyone. And what are the two methods? Computational fluid dynamics and wind tunnel testing. Okay. Now moving upon subsonic aerodynamics, it's the same thing that we are talking about the wind tunnel and its fundamental applications. This is the method how people used to test a model back in the days. That in uh, let's just say in 1900s, people used to actually create a tunnel, and they used to place the whole model of aircraft. Now this was obviously not feasible for companies to do that, even airlines moreover, because once you're doing that, there's a chance that you might hamper or create a problem with the models or the hydraulics. So instead they started using the prototype or the scaled down versions, which are much better, and it's just the scaling ratio which is being changed. Even though the Reynolds number or the flow regime is different, at the same point, previously this sort of method was being used. As you can see, that the height at which it is kept and the human which is being there to visualize or make sure that all the hydraulics are kept properly. Now regarding supersonic aerodynamics. Now, this is the place where aerodynamics is totally getting changed, right? Because as of now, it's just discussing regarding flow and the types of flow and how it is going, that compressible and incompressible. Up to subsonic, the flow is very simple, right? There isn't much change to it, there isn't much thought process to it. But the moment we are going up to supersonic aerodynamics, that is the flow over a delta wing, particularly any sort of fighter jet comes under supersonic range, that is Mach 1 to Mach 5, moreover. and usually an aircraft goes up to 3 to 4.5. There isn't an aircraft which has reached Mach 5 in the supersonic range. Now, in supersonic aerodynamics or any sort of delta wing, as you may say, there are three regions due to which vortices are being generated. There's the trailing edge vortices, and there's uh, the sharp edges due to which the vortex is being created. When we're talking about supersonic aerodynamics, we also include thermodynamics, the fundamentals of it, more because of the fact that the moment we are talking at supersonic, the speed of sound is being subdued or it is getting reduced. It is not being used as a reference. We are going above the speed of sound. So the moment we are disbarring it, we are obviously going to get disturbances, and those disturbances are in the form of pressure and thermal energy. And that is the reason why we use thermodynamic relations, that is isentropic relations, and other pressure temperature relations in order to guess how supersonic aerodynamics works. Right? Supersonic aerodynamics also is used in missiles and spacecraft designs. So you can see that in the next slide. Yes. So talking about sonic booms or moreover shock waves. Um, okay. So in the movie Top Gun Maverick, that is the second part, we saw a hypothetical aircraft known as Dark Star. I'm not so sure whether it exists or not. I'm going with the term hypothetical. And at a particular speed, that the jet which is there, it gets transferred from the normal jet engine to the ramjet or the scramjet particular part. And once it happens, and Mach number is getting increased, right? So once the Mach number is getting increased, there will be a particular point at that particular region where you will get a disturbance and you're going to break the sound barrier. Now, what is sound? Right? We obviously hear that sound is we are hearing the sound of any particular AC or a fan. But what is the meaning of sound, moreover? We don't need a proper definition from dictionary or something. Anybody can just explain like what is the meaning of sound, moreover.
It's a vibration which propagates through medium, such as air.
And then what is a sound wave? There are three terms that I'm going to be discussing: sound, sound waves, and speed of sound. Right. So first, sound. It is pretty clear that sound is a vibration which is being observed in any sort of medium, that is particularly air. And then talking about sound waves. So if this is an activity which is being done or even shown in movies, that there's a lake or a pond and a person will throw a stone into it, right? So that sort of wave disturbances is something moreover observed in sound waves. It is moreover like a series of disturbances which are being observed in a medium, and that is sound waves moreover. And when I'm talking about speed of sound, there's a slight difference between sound waves and speed of sound. That when those waves or sound waves are particularly traveling in a medium at very high speed, we characterize it with the help of speed of sound. Now, in particular calculation, we use speed of light for calculations, and in aircrafts we use speed of sound. Now, the reason why Mach number and speed of sound is very much related or required, because once you're trying to create or break the sound barrier or create a shock wave, there's a high amount of drag acting on the surface of the aircraft. The moment a shock wave is being created, your aircraft is going to undergo a lot of turbulence, right? And it could be very much harmful for the engine as well, because once it is going at that high amount of speed, the there can be no motor parts, like turbine cannot be installed for a very highly speeded aircraft. It is usually a CD nozzle or something like that for wait, I can even show you regarding that for scramjet engines. Yes. Okay. The thing which I forgot was the inlet body, or it's a diamond-shaped thing. Just a minute. Yes. Is this visible to everyone? Yep. Okay. So as you can see, this diamond-shaped thing, it's a basically placed at the inlet of any sort of aircraft which is going at a very high speed. Now, this particular shape or this particular body, what does it do? That when flow is moving across it or on it, it creates shocks. These are very small amount of shocks which reduce the Mach number surely, but there are two types of shocks which are being observed. First is the oblique shock, and second is the normal shock, right? So if I have to discuss about oblique and normal shock, it's a simple representation. Normal, that is being right? So if there's any aircraft which has a diamond inlet body, the shock will be perpendicular, right? And oblique will be inclined at any angle. Now, the reason why means as engineers we prefer oblique shocks more than normal shocks. Normal shocks are very much detrimental because at the inlet, as you can see over here, the Mach number is greater than 1, right? If by any chance we observe a normal shock, which is perpendicular, the flow gets separated and your Mach number drastically reduces, right? Now, just to give an example, yeah. So if the flow at the inlet is going at a, let's say, a Mach number of 3, okay. In the case of a normal shock, the Mach number is going to get from the supersonic range to the subsonic range. That is the amount of detrimental effect of a normal shock. But in the case of an oblique shock, if the Mach number is around 3, and once the oblique shock is being observed, the Mach number can maximum go to 2.5. It doesn't go below it. So in that case, both of the shocks are harmful for the body. At the same point, we prefer oblique shocks more, so that the Mach number doesn't get reduced drastically, but at the same point, the aircraft can continue moving at supersonic speeds, right? So the diamond central body and what is its importance in any sort of engine is clear with everyone. If there's any doubt, yep. Okay, sure. So this sort of diamond central body is even observed in scramjet and ramjet. In both the engines which are going at very high speeds, we observe this sort of structure, and it is very much required to create high amount of thrust. Now going back to the presentation. So that is all about supersonic aerodynamics that we are discussing as of now. That shock waves are more or like the pressure disturbances which are created when Mach number is greater than the speed of sound. And the two types of normal shock, the two classification of shocks that we have is normal shock and oblique shocks. Now, hypersonic aerodynamics. Does anyone have any idea, any hypersonic aircraft which is being observed? Or any example, moreover, of hypersonic aircrafts or even rockets?
X-43.
X-43, yes, that's correct. Okay, wait, my screen isn't being shared. Yes. X-43 is the classic example, or the ones which are being worked upon for hypersonic aerodynamics. And it is also failing terribly. The reason being that an aircraft can't go hypersonic from ground. It needs to be there in the air, and it is being launched like a missile, and then it can achieve hypersonic speed. But even at the hypersonic, what changes is that because of going at such a high speed, the heat which is acting on the surface of the aircraft gets so heated up that the material can't stay, or it cannot last that long. Even for a combustion chamber, let's say the combustion chamber of an aircraft, the temperature ranges to 1800 Kelvin, right? So an alloy of aluminium can be used, or a very high temperature resistant material can be used. But for hypersonic aerodynamics, 1800 Kelvin is also a less number. The temperatures can go much, much higher to 3600 Kelvin. And that is the point where any sort of material would just rupture through air. And you don't need that when your aircraft is moving in that particular speed. And the major disadvantage being that you cannot take a hypersonic flight from ground. So these are the two things that are being worked upon. And the one which you can see on the right, that is the thing that people are actually working upon. And these two are the examples for hypersonic aerodynamics, or the hypersonic aircrafts, moreover. The reason why we don't have much information for hypersonic aerodynamics, because it is currently in research. It involves much more than aerodynamics or thermodynamics. It requires much more amount of research and study. And for anybody to last at hypersonic speeds, the person sitting inside it as well needs to be, catered to that particular speed. Uh, does anyone know which is the fastest amount of G-force experienced by any human? Okay. What is G-force? Just a minute. Please dwell on G-force in the meantime. Yeah, sorry. Okay, so G force is basically the gravitational force acting on any particular object. Now, when you are, flying an aircraft, that is moreover like, let's just assume any fighter jet, the G force which is being experienced by any sort of pilot ranges between 3 to 5 Gs. The maximum a human can take or undertake, moreover, is 10 to 12 Gs. After that, you will undergo brain injuries and serious injuries which you can't recover from. So 12 Gs is the maximum a fighter jet pilot can take up to, but the highest amount of these which is undertaken by any human being, that is 46.2 Gs, right? This is the highest ever observed. You can go on the internet and search about him. That particular human couldn't live a long life, because once any object can go up to 46.2 Gs of force, their internal organs or any sort of structure wouldn't last for a very long time. It will be disoriented, and because of that there can be medical issues as well, right? So this is also a very big problem when we are discussing about hypersonic aerodynamics, that G force for the particular pilot, it can't be suited enough, because at higher G force humans can't sit through it, or they cannot experience that amount of G force. We'll be facing very high detrimental health effects. Okay, so is this clear with everyone? Yes. Okay. So I guess we are moving on to the last slide. That is the future scope of aerodynamics. There are three things that we're going to discuss about, and these three are currently in use or more, working upon. First is laser Doppler velocimetry. For all those physics geeks, what is Doppler effect? Anyone regarding Doppler effect? Let's just say in the sense that if you're an observer, right? Karthik, were you answering? You are on mute, actually.
Am I audible now?
Yeah, you're audible.
The Doppler effect is basically the change in frequency of waves, and it's basically the change in frequency of waves, and it's more like from the observer point of view, the change occurs.
Correct. Exactly. So it is, very widely used in aerodynamics as well, and various physics phenomena. when Doppler effect is being used, it is more regarding the transfers of frequency of waves, which is being differentiated with respect to the observer. Now, the moment we are talking about laser Doppler velocimetry, so this is a method which is an alternative to wind tunnels. Right? Wind tunnels is a method from where you can visualize the flow over any body. What happens in laser Doppler velocimetry? Um, is everyone able to see this image? Yeah. So a simple method, if I'm talking about LiDAR systems, so this is something similar to laser Doppler velocimetry. What happens is that there's a ground point or an object that needs to be referred, right? And you are there at an altitude. So laser is being transferred to that particular object, gets reflected back to you, and that particular, you know, transmission or that particular reception, with the help of that you're able to find out the orientation of that particular object, right? So this is in terms of LiDAR system which are being used in aircrafts or drones. For laser Doppler velocimetry, what happens is that we are using the Doppler effect, that is the car in this particular sense, it is moving, right? And when the, the bottom part, like that is the track, that is being accelerated more and more, you can observe that at higher speeds there's a change in the frequency with respect to the observer, and at the same point we have lasers which are being reflected upon it. When this is happening, you can see that there's a drastic change in the frequency, and with the help of that you can get more accurate results of the flow, means not about the flow but regarding the aerodynamics of that particular body, right? So this is something which is currently going under research, and people are using this in industries. It's a very expensive method to get the flow visualization, but at the same time it's very interesting. And if you get your hands on laser Doppler velocimetry, do try it once. Now the second one, that is particle image velocimetry, right? So particle physics, there's no relation to particle physics and particle image velocimetry, but I'll try my best to explain it. What is a particle, moreover? I know, quite a vague question which I'm asking right now, but when we're talking about particles in reference to optical physics, we are talking about the photons or any sort of particle which is being transmitted in a ray, right? Now, in the case of particle image velocimetry, what is happening? Yeah. Okay. So let's just assume you have taken any sort of object, and the flow is being going over it, right? The moment the flow is going over it, we have taken a controlled volume or a region upon which laser is being transmitted. Now, a camera is also set up in the manner that when that sort of disturbance is being observed in that particular controlled volume, you can see that the particles are getting disoriented. In the video that I had shown you previously, particle image velocimetry was also used because it's more regarding the use of light, lasers, and particles. And we can use all those three mediums to find out what is the disturbances and how we can observe the aerodynamics flow over it. Right? So this is very simple compared to laser Doppler velocimetry, because in this we aren't using lenses or any sort of reflectors. We're directly observing it with the help of lasers and the camera, and that is the flow after the error for any sort of object. Right? So is particle image velocimetry clear with everyone? Okay, so the last thing which is there for today, that is aeroacoustics. Now, we have been discussing vastly the relation between sound and aerodynamics, right? We have been seeing that even for Mach number, we are using speed of sound as a reference. Now, when I'm talking about acoustics, what does the word acoustics mean?
Something related to instruments, as far as I know.
We have very good artists over here. They're discussing about instruments. Yes, acoustics. Any general idea apart from that, the instruments part? Aditya, Navya, Sona, if you guys wish to give it a try.
Anything related to sound, as in transmission, receiving, and all those things.
Okay. Okay, that is, you know, regarding transmission reception, yes, that is more correct. And it is more like an effect of sound, if I have to explain it in that sense, that when I'm talking, the medium is air and the waves are being transmitted, right? That sort of transmission and reception is an acoustic. So when I'm talking about aeroacoustics, it's more like aerodynamics combined with that sort of acoustics. And the reason why it's important, aeroacoustics, is when an engine is moving at very high speed, it's going to create noise, right? If you ever stand on the tarmac, you can see when the engine is getting propelled or any aircraft which is getting docked down. You can hear the sound of the engine, and with the help of the sound of the engine, you can assume or know how what is the efficiency. This is an actual fact that pilots who are very much experienced, or even AME engineers, even with an aircraft which is flying at 36,000 feet, if they're able to hear the engine sound, they can know how much it can last and what is the maintenance which is currently there. The more smooth the engine is propelling or it is being used, it is better, and at the same point, lesser amount of noise implies that the engine is in good condition, right? In any sort of machinery, even if you're talking about an AC, if there's any sort of disturbance, if there's that the acoustics purchase is getting messed up, we can know that the AC, that particular air conditioner, is out of service or it requires maintenance. In the same manner, while we're talking about aircrafts, that particular turbine or rotatory part are the engines, right? An engine consists of a turbine, which is a moving part. The moment we are keeping a moving part at very high speeds, there are chances that there are going to be disturbances, and with the help of that sound, you can understand whether that engine is in good condition or not. So aeroacoustics moreover deals regarding that sort of part where we are able to discuss or understand whether that particular sort of rotatory part or the engine is in good condition or not. The reason why it is currently in study is because that right now it is being used for engines. Later on, even for cars or any sort of smaller mediums, we'll be using aeroacoustics, and it is a very big concept of study, because the more you understand about the relation between aerodynamics and sound, the more you can understand why sound is being propagated in that particular medium, and why at higher speeds you're not able to hear the sound of the engine or moreover, right? So do discuss or research about this. Now this is the end of the PPT. If you guys do have any doubts, you can surely ask. It's not particularly about aerodynamics, but about other topics as well. There's a small demonstration also I wish to give regarding of the G-force which I was talking about. And if you guys have any doubts, we can discuss that and then move to the software.
I just wanted to know that
Mhm.
what was the highest G-force experienced by a human?
What is the highest G-force?
Experienced by a human and survived.
46.2 Gs. I can even explain the mechanism of how it was done. So it was basically a chair and a track, right? It was placed on the chair and it was launched on a single transverse manner. And once he had consumed that 46.2 G force, that particular chair was put on a stop. Now imagine you're traveling at that particular high amount of speed, and the craft or any sort of moving object just comes to an halt. That is the moment when that particular human experienced 46.2 Gs of force. You can surely read about this, and
Yeah.
G-force is very much harmful for any sort of human or even in general, because that is the major concern for hypersonic aerodynamics, that if you're able to tackle G-force or a way to make a volume in which G-force isn't being harmful enough for humans, then we can surely go for supersonic or hypersonic aircrafts.
What is the simple explanation of G-force? Like the most simple explanation.
Okay. Okay, sure. G-force, if I have to explain in the most simple manner, that let's just assume that a human is going from Earth to space, right? Now, when the aircraft is moving, it is obviously not moving at a very slow speed. It will be moving at a very high amount of speed. Now, when that speed is going above the speed of sound, you're experiencing G-force. G-force comes into place when you are going above Mach number 1. Below Mach number 1, that is subsonic region or transonic region, you won't experience G-forces. It will be very negligible. But the moment when you're going in the supersonic region or hypersonic region, you're experiencing G-force. G-force is more like a consequences of higher flow regimes that is greater than 1 or in 5 to 10 region. I hope that clears it out.
Yeah, thank you.
Yep. Any other doubt? Not in terms of aerodynamics as well, but in general, like science, physics, astronomy, particle physics, whatever we could talk about. Any relation between any of the topics? Okay, so in the meantime, I'll just go with the fusion thing. Okay. The thing which I was talking about, G-force, I can just share it right now. Is this visible to everyone?
Yes, yes.
Yeah. So recently, I was on an internship which was regarding CubeSats. So CubeSats are basically small satellite structures which are in the ratio of 10 by 10 by 10, 10 centimeters moreover. And it is so small that you can send around 70 small nano satellites in one go, 70 to 150 range. Now, this sort of simulation which you can see over here, that is a 10G force acting on such a small amount of satellite structure, right? So over here you can see the different modes. That is the amount of hertz. Hertz is moreover way we can measure frequency, and this is the amount of frequency up to which this particular structure can last in high amount of G force. If I have to animate this particular thing, yes. So once the satellite structure is going at very high amount of speed and it is experiencing G force, you can see there's a deformation in the structure. This is basically due to the 10G force which is acting upon that particular structure, and we can see this deformation. This deformation at some points it is harmful for the structure as well. At the same point, any sort of satellites or payloads have to undergo this amount of force when it is being traversed from Earth to space or even low Earth orbits, moreover. Right? So this was the thing that we have worked upon. This is just one simulation which we had done, that is regarding the 10G force. If I have to talk about static stress, static stress one isn't working. Yes, for thermal, yes. So, in case of any payload or satellite, if you are working upon it, thermal stress is very much required as well, because the even though there's a rocket body which is being present outside, and you have the casing under which the payload is present, when it is being launched into space, you need a particular amount of uh, limit up to which that temperature can be, restricted or tolerated. Right. So the maximum temperature of this particular structure can go up to 250 degrees Celsius, and the minimum is minus 169.1 degrees Celsius. So this is a very good range for any sort of satellite, and this is a very small satellite. So in that sense, this is a very good high range of number. And thermal stress, vibration test, these sort of stress also come into computational fluid dynamics. So in this case, this is a very good start which you can go for, right? So that is it for today's session. This is all the things that I have to discuss about aerodynamics, CFD, and if you guys have any doubts, you can surely ask again.
As I noticed that in this satellite, on the sides, it is like a triangle shaped, like hollowed out, and it's awfully similar to Iron Man's arc reactor. So,
Yes, that is the whole surface, reference that we have used the arc reactors design. We humbly say that we have copied him. There's no harm to that.
thought that it was some advantage for the
No.
structure. So it's a reference.
Yeah, it's just that for any sort of small structure that like that of a satellite, you are using any sort of shape or a design on the surface. Now, this particular one, the satellite which we made, which was 3D printed. Now, in any general idea, if there's a solid surface and if there's a surface which has holes in it, the one which has hole will be more lighter and durable rather than the solid surface, right? That is the moreover idea of designing the surfaces of any CubeSat. That is the one which we went ahead with.
Yes, yes.
Okay, apart from the Iron Man description, any other doubts?
What material did you use? Plastic or anything else?
It was the PLA filament which was being used. That is the classic for 3D printing. And I'm not sure about the specifications, but yeah, it was a PLA filament.
Thank you.
Okay, so if there are any no more doubts, so we can surely conclude the session. Is that fine from Hex-Star's side?
Okay, I think that nobody is having any other queries or questions. If you have, please do ask them right now.
Yes.
Okay, so before everyone leaves, I'm just giving the link of Extra Universe website. And as you guys are interested in CubeSats, so you can go and check out our CubeSats that we make. We make pre-built CubeSats. You can go and check out the CubeSats. The link is right here. And for more courses, you can also visit there for more free sessions. You can stay tuned with us. And thank you, Raahil, for this wonderful session. And thank you to all the participants who have taken the time to join.
Thank you, Arudra. I hope I pronounced your name correct.
Yeah.
So
Thank you,
thank you, everyone. It was a delightful session. Thank you for bearing for me for the past 1.5 hours, talking about aerodynamics and Iron Man, probably. And yes, in case if you have any doubts, you can surely get in touch with me. And Extra is a good platform where you can learn about different concepts. I have attended their 2 masterclasses, which was about CFD and satellite masterclass. So both of them are really good. Do check it out, and you can learn a lot through it. That's it from my side. Thank you, everyone.
Thank you.
Thank you, everybody else. You may leave now.